Yeah, my dear students, this is Professor of Thermal Engineering. This is the fifth part of the first unit. So with this, I'll be finishing the first unit. As you know, this is a vapor power cycle, and today we'll be dealing with the regenerative Rankine cycle. Regenerative Rankine cycle. Already we have seen standard cycles, auto, diesel and fuel cycle, and in vapor power or steam power cycles, we already seen Rankine. And the improvement in Rankine, one way is to reheat it, and the second part is to regenerate the steam or the feed water before it goes to the boiler. It is heated again, regenerated, the heat is regenerated. So that is a concept here. So we will see about that. So in the ideal regenerative cycle, you know that the efficiency will go down if the temperature is, or what I'll say is the mean temperature of heat addition is very low. If the mean temperature of heat addition is very low, that is likely to be, the efficiency will be likely to be very low. So how to improve the mean temperature of heat addition is the concept. Once we did it by reheating it. So here we will be talking about how to increase the average temperature of heat addition. So the next method is by regeneration. So we will see about regeneration. The regenerative cycle is, you can see that there is a feed water heater. So the word is feed water heater. Is water before it enters into the boiler. Before it enters into the boiler, it has to be heated. So normally this unit will be absent in Rankine cycle. If you look at Rankine cycle, this unit will not be present. So we are trying to heat the feed water which is coming from the condenser. Before it goes to the boiler, it will be heated. Thereby, we can improve the temperature. So raise, what is the concept behind is raise the temperature of a liquid leaving the pump, or I mean the feed water. Raise the temperature of feed water before it enters the boiler, so that we can improve the mean temperature of heat addition. If the mean temperature of heat addition is increased, the boiler efficiency, the power plant efficiency will improve. So how it is done is we are bleeding. Bleeding means taking a small portion. In reheat, we take the entire steam to be heated again. Here we take a small portion. So for example, if it is 1 kg of steam is coming here, we take around mkg. Mkg be around 20%, maybe 200 grams of steam is bleeded, taken from the turbine, and that is used to heat the feed water. So that is given to the feed water. It's a open feed water heater. It mixes with the liquid water and steam mixes together. Thereby the feed water temperature will be increased from, say for example, T5 to T6. The temperature has been increased. Thereby the average temperature of heat addition is pushed up. Thereby the efficiency. So the device where the feed water is heated is called as regeneration, or we call it as feed water heater. So that is the concept of regenerative Rankine cycle. So you can just remember it is very easily. A feed water heater comes into play. Okay. So how to represent here in a TS diagram? Always TS diagram is very easy to remember, and it gives a lot of information. So you can see that point 1 is steam coming out from the boiler at a high pressure and high temperature. It is expanded, and you know that it is a reversible adiabatic expansion. Entropy is constant, that is S1 is equal to S2 is equal to S3. You see here, because it is a reversible adiabatic process or isentropic process where the entropy is constant. And partially, after expanding from 1 to 2, you can see at a point 2, a small portion, mkg, let us say, 0.2 kg or something, mkg of steam is taken out, and it goes directly to the feed water. So what is the balance which is coming after 0.2 is 1 minus m. 1 minus m will be coming from 2 to 3 to the condenser because m is taken directly to the feed water heater. So this is how the schematic diagram, and you can see how it is represented in the TS diagram. So you can see that only 1 minus m comes to the condenser because m is taken out, and 1 minus the m kg of steam comes to the condenser, and that the same thing comes to the feed water pump here, and at 0.5 also 1 minus the m kg will come, and from 0.2 m kg comes. So 1 minus m plus m, then what it goes out from 6 is 1 kg because the m will be added with 1 minus m, so you will have 1 kg at 0.6. This is a schematic diagram of a regenerative cycle. It is always good to remember the TS diagram and HS diagram for these cycles. So let us see how the energy conservation is done in the feed water heater, because our point is the regenerative cycle is the regenerator or the feed water heater. So you can see m kg is bleeded from the turbine, 1 minus the m kg is coming from the condenser, and again here 1 kg goes back to the boiler or the feed pump. Energy conservation is energy entering is equal to energy leaving. There is a law of conservation of energy. So what is coming in? You can see that m into H2 enthalpy. M into H2 is coming in, arrow mark, look at the arrow mark, it is coming into the feed water heater. Similarly, you can see that H5 into 1 minus m, or 1 minus m into H5 is coming in. And what is leaving is H6 is leaving. So you can just multiply the m into it. You will get m is equal to H6 minus H5 divided by H2 minus H5. This is how we calculate the mass of steam which is bleeded. So this formula is very important. If you remember the diagram, you can put this equation. Otherwise, you have by heart this formula. It is H6 minus H5 divided by H2 minus H6. You have to remember somehow. If you look at this is 0.6 minus 5 divided by 2 minus 5. So this is how we calculate the mass which is bleeded, mass of steam bleeded, which will be normally asked in the problems. We are going to see how to solve the problem here. The TS diagram also you keep it in mind. So normally they will ask 1 feed water heater. We can have 2 feed water heater also. That is the scenario here. In regenerative heat exchanger, you can have 2 feed water heater, heater 1 and heater 2. You can see that m1 kg is bleeded here. So 1 minus m1 will come from 2 to 3. Again they take m2 out. So what will be here from 3 to 4 is 1 minus m1 minus m2. So that is how it is represented here in this TS diagram. You can see. So for the time being, I'm not going to deal with the 2 heater scenario. Normally for universities they are asking. For UG students, it is 1 heater scenario only. So we will see a problem with 1 regenerative feed water heater. So here comes the problem. Okay, this is an university problem, quite often asked. So you can see the inlet pressure is 3 megapascal and 400 degrees centigrade. Once the pressure and temperature is given, you can know that it is a superheated conditions. You can use the steam table to find out the superheated from the superheated tables. I recommend that you use a Mollier diagram again to make it easy, make it fast, and you can avoid errors because you don't consume much time. At least to calculate H2, H1 and H3. These 3 points you can straight away take it from the Mollier chart. That is what I will recommend. But you remember the TS diagram. That is easy. So let us see the given data. So they have given is initial pressure. P1 is given as 3 megapascal. Mega is 10 to the power of 6. To make it into bar, divided by 10 to the power of 5, you will have 30 bar. That is why you can use it in your Mollier chart. temperature is 400. Then you can see the sum quantity of steam. The sum quantity we have to calculate. Okay, the fraction. That is a mass, AM1. Leaves the turbine at 0.6 megapascal. So that is an intermediate pressure. 0.6 megapascal. 0.6 into 10 to the power of 6 divided by 5. 10 to the power of 5 is 6 bar. So P2 is 6 bar, and you can have the condenser pressure. Here you can see the condenser pressure is given as 10 kilopascal. 10 kilopascal. So that is why it is 10 to the power of 3. 10 into 10 to the power of 3 divided by 10 to the power of 4. You will get it as 0.1 bar. So this conversion is very important. From Pascal to bar, then only you can use it in the Mollier diagram. Okay. So let us understand how to use the Mollier diagram. Similar way we can use it for Rankine and reheat also we have used the similar way. That is the same thing we will follow here also. And mass is per kg of steam, so the mass we will take it as 1 kg. Okay. This is a Mollier diagram which I just drawn for you to understand. So the initial pressure P1 is given as 30 bar and temperature is 400 degrees centigrade. You take the 30 bar line and just find out the intersecting point between 30 bar and 400, that is your point 1. Move towards horizontally to the left or right, you will get a H1. So H1 is 3230. You can use your steam table also, if you can use it, but straight away you can take it from the Mollier diagram, that will be easy. So from point 1, you take a scale and vertically move down. You move vertically down, So if you move vertically down, because you know that S1 is equal to S2 equal to S3, which is 6.9 from the Mollier diagram. So when you move vertically down, you see where it hits the 6 bar line. The intersecting point of the vertical line with 6 bar line is your point 2, and straight away move horizontal to the left or right of the Mollier diagram, and you will get the value of H2. So let us take H2 is 2630. From the Mollier diagram you can straight away read it. So let the same vertical line proceed down to 0.1 bar. If you take it up to the 0.1 bar and you find out the intersecting point where it hits the 0.1 bar, maybe inside the dome. So there, from that point, you can move horizontal to find out the value of H3. H3 you can find out as 2195. These three values, H1, H2, and H3, you try to take it using Mollier diagram. That will be very easy. Without any confusion, you can straight away calculate it. Other points, because you have to calculate H4, H5, H6, and H7, other 4 points you have to calculate. So for that, let us, there is no other option, we have to go for the steam table. So for that, it is better to have the TS diagram. So what is point 4, H4, how to calculate it? H4 is at saturated liquid line. What is the pressure? 0.1 bar. So 0.1 bar saturated liquid. So you know that H4 equal to HF. Then we need to calculate H5. 4 to 5 is your pump port. We have 2 pumps. Of course, we got a pump. So let us take, we have an equation in terms of enthalpy versus pressure. So H5 minus H4. H5 minus H4 is equal to V4 into P5 minus P4 into the power of 2 in order to convert from bar to kilonewton per meter square. And remember this P5 is P6, which is nothing but P2. For our case, it is 6 bar. Okay. Similarly, you can see that P4 is nothing but it is P3, which is 0.1 bar. So this is all the data are available, and V4 is nothing but VF, saturated liquid at 0.1 bar. So once that is found out, you will know that H4 minus H5 value, you can calculate it. H4 minus H5 value is known. From that, you can calculate the value of H5. you see the difference between these two things is very minimum, only 0.596. That's why most of the time it is very negligible. So that is how we calculated a H5. If you find it still difficult, you take H4 equal to H5. There won't be much difference. In some cases they will say neglect pump work. In that case you have to take H4 equal to H5. Okay, let us move on how to calculate H5. H6, okay, H6, you can see that H6 comes at the saturated liquid line at 6 bar, so it is enthalpy of the saturated liquid HF. Straight away you take it from the saturated steam table is 670 because at 6 bar. So the similar procedure, H7 minus H6 is V6. V6 is nothing but VF at 6 bar. V6 is nothing but VF at 6 bar. And from that you can calculate H7 minus H6, that is 2.642, so that you can add with the H6 to get the value of H7. Now you see that we have calculated 1 and 2 and 3 is a Mulling diagram. 4 is nothing but HF at 0.1 bar. H6 is nothing but HF at 6 bar. And this 0.7 and 5 we have calculated using this equation. So once all the enthalpies are known, writing the answer is very. We have calculated all the enthalpies, and that we H1, H2, H2 up to H6. We have calculated. So this diagram I asked you to remember, is it not? What is AM is H6 minus H5 divided by H2 minus H5. So that you have to by heart it, otherwise you have to use this energy balance equation. Okay, it is H6 minus H5 divided by H2 minus H6. So you can calculate the value of AM. AM, as I said, it is around 200 grams or 196 grams, 0.1996 kilograms. Okay, so let us look at the answer. Efficiency of the cycle. Efficiency is we have to calculate the turbine work. Turbine work, you remember, from 1 to 2, 1 kg of steam is coming. So that is why 1 kg into H1 minus 2, higher minus lower, plus, because M is removed here. From 2 to 3, remember 1 minus M is coming from 2 to 3. So again H2 minus H3. This is how we take the turbine work. So that is why it is always important you remember the TS diagram. M is taken out, so it is 1 minus M into H2 minus H3. It is easy to write the formula. So that is how we will get the turbine work. So pump work, we had 2 pump works, because 4 to 5, then 6 to 7. 4 to 5, you remember what is the mass of steam which is coming? It is 1 minus M. So it is 1 minus M is coming in 4 to 5. Then of course in the water heater, the things are added together. So from 6 to 7, it is back to 1 kg. So this is very crucial here. So if you put together, it is only 3.12 is your pump work, which is an addition of 1 and 2, pump 1 and pump 2. So net work net is nothing but it is the turbine work minus the pump work. So you will get the net work. And heat added, heat supplied is here, only 1.721 is heat addition. Here we will add the heat, Q1. Q1 is the heat addition. It is a higher enthalpy minus lower enthalpy, H1 minus H4, because mkg is involved. Heat supplied, so efficiency is work net by output by input. Output is work net divided by heat input. That will give the efficiency. Hope you have understood it. Try to work out more problems. Just try to go through the university problems. It is similar, nothing else is asked. Just don't listen to it. Go through your steam tables, Mollier chart, see whether the answer is coming or not, and give your comments. I have spent some time, I have taken some efforts for the first unit. Hope you have understood. I will come up with the next units also, I'll try to put some theory portions from IC engines. Hope you will get benefited from this. Thank you for listening. Have a nice day. God bless you.